welcome back to Engineers Workshop. So when we left off last, we were talking about the Skinner steam engine and flywheels in general. Got a comment from casting iron engines. One comment, biggest comment I've ever gotten. And it's actually 12 questions and observations that really make the basis for a little bit more in-depth discussion on this. So instead of responding to the comment, I'm just going to read this and we'll wing it. So Casting Iron Engines writes, I have read a number of the old steam engine design books, and while I understand steam engine dynamics better than I did initially, I still don't feel like I have a complete understanding of all the forces and power transfer involved. A few things I have read, check me on all of these. Number one, most of the work occurs in the first quadrant, i.e. from a crank position with the piston at top dead center to a crank at 90 degrees. Correct. Now there's a little bit more to that than meets the eye. So basically your crank throw is rotating about its center line, and then the connecting rod comes down from that to a crosshead slide, and that is basically what's receiving the forces from the piston in both directions. So that force gets transmitted up the connecting rod, and at this point you got to look at that force as it has a component that is a torque on the crankshaft, and it has a component into the crankshaft which does no work. That angle is continually changing. So when we are dead straight, in other words, piston at top dead center and crank horizontal, that force has no component that tends to rotate the crank. So the force is zero, builds to a maximum some point up here, and then as the crank would be, I'm drawing it as if it's rotating in this direction, as the crank passes some point of 90 degrees, in the Skinner steam engine, the steam is cut off and the pressure in the cylinder just expands from there. So the force starts to decrease, and then at some point the exhaust port will open, maybe when we're back here, and the steam will dump out of the cylinder and the force will drop to zero. So the torque as it applies to the crank, it's going to start at zero, build to a maximum, start to taper off basically, and then fall off a cliff when the exhaust port opens and dumps. And all of that will occur 90-ish degrees. Number two, the maximum acceleration of the flywheel is during the first quadrant. Most likely also true. Maximum acceleration is going to be when the force acting 90 degrees to the crank throw is at its maximum. Number three, the velocity of the piston rod, and crosshead are zero at front dead center and back dead center. That is true. Number four, balancing a steam engine is a trade-off between balancing the vertical forces and the horizontal forces. The connecting rod creates a vertical force because one end of it swings up and down. The piston rod, and crosshead create horizontal forces, and I think part of the connecting rod weight does also. The crank pin creates an unbalanced force as it rotates. All of that is true. So basically, when you're trying to balance an engine, one way to do it is to have your flywheel, and you've got some mass of a piston, connecting rod, crosshead, and the horizontal component of a relatively heavy connecting rod that goes back and forth. Now, as this approaches front dead center, you can put a big counterweight on the crank out here, so that the velocity and the mass of this counterweight, the horizontal component, matches and opposes what's happening with the piston. Actually, this one will be going this way. You can do the math, and you can just about completely balance out the horizontal forces of that counterweight and horizontal forces of all of your components moving this way. But what this does then is, in the up and down direction, it's going to be putting force both into the foundation and up here. It's going to tend to be lifting the engine off of its foundation. So it's going to put a hop on the engine. Now, will that force be enough to actually lift the engine off the ground? It could be. Most of these engines are pretty heavy and run slow enough that I don't think it does per se. But this type of counterbalancing to counterbalance the horizontal forces introduces a vertical component that you can't easily get rid of. So that was number 4. Number 5, the point at which the exhaust port closes, compression, is important since this allows pressure to build up in the opposite end of the cylinder to cushion the reciprocating parts and allow the transfer of forces from one side of the crank pin to the other. The energy in this compressed exhaust is returned to the engine since it increased the pressure in the cylinder just prior to admission. I've read quite a bit about this, and in my mind, the jury is still out. Because when you have a crank pin, and let's say the crankshaft is at 90 degrees, and we're coming up like this. So we've got a crank pin here that until this point has been pushing and accelerating the connecting rod and the piston. So it's loading the front side of the bearing. It's squeezing the oil between the bearing shell on the connecting rod and the crank pin. Now, as soon as we pass front dead center, or let's say a 90-degree crank position, now this piston is pretty much at its maximum velocity. So it's going to cause this to swap sides. And if I were to blow this up, if we look at a big blow up of the inside bore of the connecting rod, the crank pin with its minute clearance, I'm going to greatly exaggerate the clearance, is pushing against the connecting rod. And so it's squeezing the oil film on this side down to nothing. But once the crank is at 90, now the velocity of the piston and the connecting rod and all of that is at its maximum. So the crankshaft has to start doing the job of slowing down this whole system. And so the crank pin swaps sides and then basically starts bearing against this backside. This is where the energy of the moving piston, connecting rod, crosshead slide begins to pull on the crank and put energy back into the system. So now we've taken the oil film, which was compressed on this side, we've swapped sides, and now we're squeezing the oil film on the back side. And the cushioning effect that they're talking about is basically what's happening here at the end of the cylinder. But at the 90-degree position, when this crank swaps sides, there's no cushioning. If we were to allow this piston to come all the way around to the front of its travel, and everything's in line, the crank pin would be back here. Because during this entire portion of the stroke, we're compressing the oil film by the action of the piston, and we're slowing down the piston, so it's pulling on the crank. So the oil film stays here, and as the crank continues on past front dead center, this does not swap sides. But we admit steam to this system, and they're saying to admit steam before front dead center, which would artificially begin to shove the connecting rod, which is the big circle, until it's in contact with the connecting rod, so it would move it, it would shift it over to here. And I'll tell you, the reason why I think the jury's out on this is if the engine were in good condition, the clearances in this crank pin and in the wrist pin up on the crosshead are on the order of a couple of thousandths of an inch. The clearance should never be great enough where these things actually clickety-clack back and forth. And I've seen a lot of videos of steam engines running. I mean, these things are 100 years old. It's not a criticism of the owners and everything, but they have a lot of wear. And there's a lot more clearance in these connecting rod journals and in the crosshead slide pins that there's significant amount of slop. And you'll hear the engine clicking, and sometimes I've even seen some where the crankshaft is physically moving back and forth in its bearing shell. You can see its relative motion. Nothing that is set up correctly should have that much motion, and I think this cushioning effect is a little bit overrated. When the governor of the Skinner engine begins to govern in it and it narrows its window of operation, it's not emitting steam before front dead center, so there's no cushioning effect at all. So number 6, in his book, Charles Porter, Engineering Reminiscences, mentions that the more mass the reciprocating parts have, the smoother the engine would run, even if the crank bearing bolts were loosened. He struggled to explain this phenomena, but demonstrated it on running engines. More mass the reciprocating parts have. I'll tell you, the more mass the reciprocating parts have, the harder the engine is to balance. They do have somewhat of a flywheel effect, so this piston and its system moving linearly helps to keep the engine in motion once it's in motion, but I don't know if that statement is 100% accurate. Number 7, at low RPMs, I'm not sure if much consideration was given to balancing steam engines. The higher speed steam engines sometimes had counterweights on the crankshaft, but often did not. As the RPM increased on steam engines to what was considered a high-speed steam engine, i.e. 300 RPM, balance would have been more critical. Porter does not seem to mention balancing his engines. Balance is more critical at higher RPMs. The accelerations get higher, the forces into the foundation get higher. It's trade-off. How much mass is there in the frame of the engine itself to absorb all this? For a single-cylinder horizontal reciprocating diesel engine, the recommendations are on the order of the foundation block that the engine is attached to should be 3 to 5 times the mass of the engine. So in the case of the Skinner engine, you're talking a 5,000 pound engine. So 15,000 to 20,000 pounds, 25,000 pounds of mass in the concrete to help absorb the vibration that the 80-some pound mass of the reciprocating system generates. That's what we're looking to do. Number 8, some of the power is lost in bearing and other friction, steam, condensation, etc. That is true. Number 9, there would be significant forces generated on the bolts holding the engine to the concrete base, both horizontally and vertically. Also true, unless the speed of the engine were running such that the mass of the engine would prevent it from sliding back and forth. My Skinner is on a rolling cart, and we'll see real quickly when I get it running, if I can get enough speed in it, if it starts to shake the rolling cart back and forth. Number 10, Porter greatly reduced the size of his flywheels from what was standard at the time because the larger flywheel would probably not survive rotating at 300 RPM, and because at 300 RPM a smaller flywheel could be used successfully. Semi-true. The energy that a flywheel stores increases proportional to the square of the speed, I believe. So the faster an engine turns, you can have a proportionally smaller flywheel and have an equal amount of variation in speed. Cast iron flywheels have a limit of about 5,000 surface feet per minute on the velocity of the rim to keep the stresses safe because the flywheel wants to burst and to stretch and burst as it's up to speed. But bigger flywheels are better because a steam engine is transmitting power through a big old flat belt usually, and if there's variations in speed, then that flat belt is getting tugged as the engine varies its speed, and you've seen the belts, and they'll just be flapping and dancing all over the place. So the bigger the flywheel, the less stress you put on the belt. Number 11, locomotives don't have flywheels per se. I guess you could consider the wheels as flywheels to some extent, but the later locomotive wheels were somewhat small in diameter compared to the earlier ones. There was a significant amount of effort put forth to balance all the wheels on a locomotive dynamically as it was running to prevent rail pounding. If you look at a locomotive, generally no two counterbalances on any of the wheels is the same size or in the same position necessarily. Yeah, partially true once again. And locomotive wheels, they were pretty big even on the latest steam engines, especially if they were high-speed passenger engines. But what locomotive wheels had that a simple steam engine did not is it had a side rod So to keep the wheels all in phase, where they had crank pins like this, you had a side rod, and these are generally segmented, rigid links, and then one of these would have a connecting rod also coming up to the cylinder. Actually, these are on center, but mass of this big side rod, you're talking solid cast iron or cast steel bars, are moving in a circle as the locomotive is traveling down the track. So all of this mass of this side rod had to be counterbalanced. And this one probably had a bigger counterbalance because it had the additional mass of the connecting rod. But once again, this is a trade-off because they're trying to balance the vertical force that this side rod is putting into the rails. But then these counterbalances, well, actually these counterbalances are always opposing the motion of the side rod. So they tend to completely cancel things out. You still have to do the horizontal motion of the piston, crosshead, and connecting rod, but those are all to balance this massive member here, and that's only on locomotives. Number 12, the flywheel size and mass can affect the governor operation, since a flywheel with too much mass may slow down the reaction of the engine to changes made by the governor. This is my understanding of it anyway. Reading books only gets you so far, though. Nothing like having an engine to try things with. I have a few steam engines. I could pull the flywheel off one of them, and it weighs perhaps 300 pounds. I'm sure the engine would still run without the flywheel. I wouldn't recommend this. But if any significant load was put on it, or any significant RPM, I'm sure the motion would be rather jerky, and there may be some excessive forces imposed upon some of the moving parts, and especially the crank pin. I guess the $100 question would be, would the engine run at all, or would the piston just stop at bottom dead center? I guess if there was sufficient compression on the opposite end of the piston at the end of the stroke, that could force the piston back up again. I have a simplex and duplex pump that doesn't have a flywheel or a crankshaft, and they run fine without them. But I guess they have a special valve gear mechanism that allows the engine to reverse direction. I've heard about these simplex pumps, and there's kind of one of those things where in theory it shouldn't work at all, kind of like a bumblebee aerodynamically, can't fly but still manages to fly. As far as the flywheel affecting governor operation, I would say improve the design of the governor so that you can still run a massive flywheel and have a sensitive governor to change speed. And I've talked about the governor for the Skinner engine. It's not so much a centrifugal governor as it's an inertial governor. It maintains a position relative to the flywheel that the minute the flywheel changes its velocity, the difference in where its position should be and the position that the governor is instantly actuates the governor. So it doesn't matter how much mass is in the flywheel. If you change the speed of the flywheel, the governor senses that, instantly dumps more steam in, and the engine maintains its speed. So I hope you enjoyed that. We'll get back on the other features of the engine soon, but this is a lot of detail about flywheels and bearings and oil films that casting iron engines asked some questions on, and hope you liked it as a basis for another video. Catch you next time on Engineer's Workshop.